so today I'm going to talk about work that I've done in collaboration with Eiko Voigt in Vienna for a little bit longer, moving to Bonn soon. And then it's actually the work of a student we co-advised, Dorian Spat, who also was there and now is at Trento. And let's start with orienting everybody. We're going to be talking about this region of Africa the purpose of this talk, we're going to call the Sahel. The Sahel extends farther out, but we're looking at the more western and central part. And I've been staring at this time series for about 20 years now. This is summer rainfall in this area, and it's been one of the most studied rainfall record because of this precipitous decaying rainfall from the wet 50s to the terrible droughts of the 70s and 80s. Since then, the mean rainfall has recovered. And so now we are hovering around the long-term mean. But we now have 40 years of satellite data. And so we can say a bit more about this period besides the fact that the mean rainfall has been going up. Especially because there's an expectation that with global warming, the character of rainfall should be changing. And so there was a paper about 10 years ago showing how the frequency of extreme Saharan storm tripled since 1982 in satellite observations. And we were looking at high resolution models, and we started out by saying, well, reproduce the Taylor et al. And when Dorian did that, we found some interesting results. But so let's start out by thinking about what are the rainfall systems that we're interested in. Yesterday, I've talked about the system, the monsoon system here with the African easterly jet and the waves and the mesoscale convective system. And so you can follow them. I go back and will this activate again? No. Okay. Well, you could follow these systems in the brightness temperature with a connecting temperature of a cold enough temperature. And these are, again, sometimes connected to these waves, sometimes happening on their own. And so we're gonna look at the temperature of the clouds and identify the regions as mesoscale convective system, everything that is colder than 40 degrees, and then everything colder than minus 70 degrees is we're gonna call it the overshooting cloud top. So color coding them here, and just to make a point that these are very important systems, and they were basically capturing most of the signal. 70% of the total rainfall comes from them, and 70% of the extreme rainfall comes from the convective towers. All right. So here is the map view of that. Precipitation fraction in percentage given by the mesoscale convective system, and for the 99.9th percentile, the percentage coming from these convective cold cores. Okay. So this is, as I was saying before, this is the interesting results. When you duplicate the work by Taylor, you find that, well, things haven't progressed quite the same way. And so we see here is cloud cover in mesoscale convective system. Here is in the cold cores. And in both cases, we're looking at two data sets. One is the long one, and one is a newer but shorter data set. But we see this strong gradient flattening out. And we had a lab yesterday about breakpoints. And so this was what those red dots are. So these are all the breakpoints that are significant. So it's not, it's not like before and after sharp changes, but you can definitely identify that something is going on. So if you take these two time series, and you find the fraction then of convection that is extreme, that also gives you this behavior, that strong increase and then a flattening or even a reduction in the trend. Okay, so this convective intensification is basically stopped. Now, the interesting thing is that the trends in rainfall have been going on just fine. So here is an increase in the summer mean precipitation. And here is the increase in the precipitation extreme. So this is, we're going from 60-ish to 120. So 69% increase actually means from the mean value of this period. But it's basically a doubling from the beginning to the end over this period of time. No hint whatsoever of any change in the slope. So no recent intensification of convection, but a continuous intensification of rainfall. Right? So here's the percentage falling as extremes. This is the same quantity that that we started out with, right? And there's no change in slope. So why this decoupling? So we're going to look at the trends in the drivers of both convection and rainfall. We start out with this well-known fact, right? That is in mesoscale convective system in particular, rainfall is going to feel both the shear, how strong the low-level shear in the U wind is, and humidity. So this is the total column water vapor, right? Which again we've been seeing prior in the presentation, the importance of humidity in the entire column, not just at the surface. Okay. This relationship works at the local scale, right? So within the storm, the local shear, the local column integrated. But now we're going to try to take, the climatologist view instead of the weather forecasting person, and we're going to try to relate these quantities, these mean quantities, to the large scale values of these of shear and humidity. So if we look at the vertical shear trend, we see that that too has flattened during these 40 odd years. And so in the first part of the record, we see a warming of the sea surface, of the surface temperature, obviously both land and ocean. This enhanced warming to the north, not so much to the south, thermal wind gradient again, and we get this intensification of the shear. What happens in the second part of the record? Well, we're still warming, right? But now the place where you are warming the most is someplace else. And so if you end up looking at the change in shear in this box, it's actually going in the other direction. All right. So the warming pattern, the details of the warming pattern matters quite a lot for changes in vertical shear and therefore for changes in the mesoscale convective system intensity. On the other hand, the moisture hasn't shown any changes in trends. It just keeps going up. So there's actually one breakpoint that the algorithm finds as significant, but it's going up before it and it's going up after that. So these are the maps. Moistening in the Sahel and moistening pretty much everywhere, including in the Sahel. And so this continuous moistening produces more rainfall for the same updraft intensity. And the other thing I want to show is that in this latter period here, 2000 to 2024, we see a moistening that is much, much deeper. You know, I mean, I guess it's much stronger, but the difference between what happened before and what happens now is that this moistening has really gone up in the free troposphere. And we haven't done a lot with it, but just because you kind of figure, you know, the large scale warming must have something to do with it. I'm just showing here the SST trends for the early period and for the late period in a couple of data sets. I'm just coming from EGU, and they were talking about new data sets in temperature. Maybe we should use the latest, but you get the basic idea. You know, we were warming mostly in the North Atlantic and the Mediterranean in the first part of the record, and there's maybe more broader warming in the most recent past. Again, as I said, we haven't done a whole lot with this. So if you put things together, right, the storm rainfall intensity, meaning the is going up. So precipitation versus the broadened the area basically of the storm was flattened before and now is going up, and the same for the intense event. There's an intensification for the same amount of convection. Rainfall is going up. Okay, and so the take-home points. Look at that. The take-home points, then, I'm gonna look about, and mine too. I wanna look about the future. And so the current rainfall recovery, first of all, you know, is getting more and more extreme. So I'm sure they're all happy that there's no drought. At the same time, this is a hard change to adapt to. And the number of strong systems depend on the strength of the local wind shear. And that is not as easy to project into the future as like, oh, generalized warming, the deserts were more than the moist places. You know, yeah, we're gonna have to do better than that. On the other hand, I think we're good with classes clapeyron. For that one, we don't really need the climate models. And so that part is for sure. Whether that's good news. All right, so this has actually been published. And so you have the QR code there, and I'm happy to take questions.
We have good amount of time for questions. Eric has a question.
So MCSs have been argued to seed easterly wave activity in this region. Do you see any changes in easterly wave activity over this period? I don't know if you showed that and I missed it.
No, but.
No, it's not. Okay.
It looks like I planted the questions. I have this slide. So we divided things between the MCSs that are overlapping, and you know, there's a caveat there of how you do it, but we decided to just do it. They're overlapping at birth with an African easterly wave, and we see the same trends whether they do or they do not. So we don't think it's because of the African easterly waves.
Yeah, my question was something similar to Eric's, like, is the convective instability sort of dominating compared to the hydrodynamic instabilities connected with these increase in rainfall and less of an organization on the MCS?
Yeah, so we didn't do that kind of analysis in part because, yeah, it really looks like it's the MCS and not the African easterly waves.
Thank you.
Okay. So I had a related question. So because you mentioned the changes are because of the changes in shear. If you look at it in terms of like the jet is it related to some changes in the jet or?
Yes, 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 yes. I mean, it's the changes that I showed in the maps were 600 hectopascal, and so then the shear is from the jet to the surface. Yes.
So can this like be looked at it from like how the jet dynamics are changing or what is changing the jet as well?
Somebody can, but we haven't done it.
I have two quick questions. One is how much multi-decadal oscillation would be responsible for these changes that you have seen? And question number two is, amidst, in general, weakening global circulation, how do we see this retrieval of monsoons?
Okay, so the first one was
So the African monsoon time series that you showed,
yeah.
seemed like there is a multi-decadal oscillation. So how much of the decadal oscillation is responsible for the revival?
So it's a multi-decadal oscillation. Whether that's natural or forced is the big question. So people have lost friendships over this. A couple of things have happened since the 50s. So we cleaned up our air, right? In terms of sulfates, and so aerosol is probably changed the gradient between the north and the south, and that would move the ITCZ. We've also warmed up the planet, and so it's possible that now we're starting to see the signal of greenhouse gases. The CMIP models can't do it when coupled. So they can reproduce this reasonably well in AMIP version, but not when coupled. And whether that's because they don't do the response to aerosols, whether they do the response to greenhouse gases wrong, or because this is an AMV signal, is highly, hotly debated. And I'm gonna stay agnostic because I'm recorded. And I think it's the aerosol planet. So the other question was, oh, okay. Yeah, I don't know. I mean, it's just regional changes are overwhelming any Heldensoden view of, yeah. I think it's not useful for prediction or for these kind of projections.
In the interest of time, maybe shall we, yes? Or do you want to sacrifice some of your time? And yes, yeah. Okay, yeah, let's thank Michela again for a nice talk.